Good evening. I welcome the viewers to this problem solving and live interaction session for the subject strength of materials. Today we will be discussing the contents of week 6, which has to do with constitutive relations as well as thermal strains and so on. So before we begin, in case I'll just introduce myself. My name is Ganesh Ramaswamy. I'm a doctoral scholar in the Department of Applied Mechanics and Biomedical Engineering at IIT Madras, and I'm pursuing PhD under the guidance of Professor K. Ramesh and Professor U. Saravanan. So let us get started. So before we start, are there any questions? Anything we need to discuss? Okay, so I suppose then I proceed with solving the questions. So let us look at this question. It says the stress strain graph shown in the figure is most appropriate indicative of indicative of the behavior of which of the following: whether the material is elastic, plastic material, elastic perfectly plastic, or linear elastic. Now, as we had discussed in the previous session also, it is the process that makes it what it is. Any material within the confines of certain loads can be classified as linear elastic or viscoelastic or elastic plastic and so on. It depends on the process. So in this case, however, we can make an observation that it initially has a straight path where the stress is proportional to the strain. So it is a straight line. Thereafter, it becomes a curve and goes that way, goes like that. So what this curve implies is uh, for an amount of strain to be achieved, we don't need to apply that much stress. That is, it is in the plastic zone, so to speak. So this essentially is signifying an elastic plastic behavior. Now, what would I think it will become more clear if we were to see how the others would look. So let me delete this. I'll just make a copy of this. So if this is elastic plastic, what does an elastic material look like? So an elastic material, if we see, although it is not qualified here, if we stretch it this way, if it goes, and then it follows the same path while unloading, it can be classified as an elastic material with no plastic deformation. On the other hand, for example, mild steel, if we take, we generally see a curve like that, and then we have a long strain hardening zone where there is excessive plastic deformation. So if as an engineer we would like to fit this to a curve essentially. So if we do that, let us say that I took this as a straight line and I took this as another straight line with no slope. So what this implies is starting from here, starting from the load initiation, as I progress, it takes an elastic path. As soon as it reaches its yield, then there is absolutely no need for increase of load for increase of strain. So this happens to be a perfectly plastic idealization of the problem. On the other hand, we know that the same curve, as we saw earlier, it actually has a path like that. When we load mild steel to the hilt, it will follow a path like that. So often what happens is, let us say this is the origin. So what treatment generally does is we will load it to this point, so much so that once we unload it, it will follow that path. And the origin or the stress-free point will get shifted there with some permanent plastic deformation. Now, if we were to take this material afresh, we can see that it follows the initial curve that we are seeing, elastic plastic behavior. Instead of an elastic perfectly plastic, it follows the elastic plastic behavior by some treatment. So all these idealizations are made so that we are able to design structures for certain using certain materials. And if we want to enhance their behavior, appropriate improvements need to be accommodated. So that is for elastic, perfectly plastic. Now linear elastic, if we are confining our attention to just this zone, if we just load it here, just enough to have it go that way and then come that way. If we are operating within the zone, then this happens to be the linear elastic zone. Although it is not exactly correct to call that a linear elastic material, initially it is linearly elastic. So it would also depend on the process, what we are saying. Because we see that all these states are attainable for the same material. For the same steel, if I take, barring this one, all the other cases can be attained for this linearly elastic. If I stretch it beyond a point, then it becomes linearly perfectly plastic. And I stretch it beyond that and then leave it, then it becomes elastic plastic. So I hope that is clear. So this would the most appropriate behavior would be elastic plastic for this material. I hope it's clear. So let us look at this question. The correct tensorial notation for thermal strain in a 3D isotropic material is what? Is what is asked. Now thermal strain causes change in volume, but does not cause distortion. For example, if I take a cuboid shape and I heat it uniformly without any restrictions, if there is free expansion, we know that this will still retain the shape of a cuboid. So this is at T degree centigrade. Now if I were to heat it uniformly, so at T plus some delta T, what we would essentially see is where delta T is positive, this would have increased this way. So what this implies is it doesn't cause shear strains. So which are the tensors which have shear strains to be 0 are our candidates. So there happens to be only one. So this is our uh, correct tensorial notation for our thermal strain tensor for a 3D isotropic material. Now this is not so in the case of coupled materials. For example, there are materials where normal stresses can cause shear strains, or shear strains can induce normal stresses. So when there is such a coupling in between them, then this relation no longer holds. Then that is when the material also becomes more cumbersome to handle. And to characterize such materials, we need to do some additional tests, which is why we are confining our attention to first isotropic materials, where the material properties are same in every direction. So I hope that is clear. So should there be any questions, please feel free to ask. Okay. So the number of elastic constants, independent elastic constants required to characterize an anisotropic material is which of the following is what is asked. Now it is discussed in the lecture. For example, when to characterize a material, in 3D space, so there would be essentially 9 stress components. As we saw, the stress tensor 3 by 3, so it's a three-dimensional space. So there is 9 stress components and 9 strain components. And we saw a number of times that from displacements we come to strains, we go back and forth between strain and stress, from where we get to forces. So presently, in this week, we are confining our attention to those relations which relate these two quantities. Previously, we saw how displacements and strains were related, and the week previous to that, we saw how for a differential element, how to write the equilibrium equations. So these are what are called constitutive relations. Now, when there are 9 stress components to be related to 9 strain components, naturally, there has to be a material property. Let me put some other, let me call this some Q, just for the sake of this thing I'm saying. Let this be some Q into our strain. So for any general material, we would be required to identify 81 9 by 9, 9 by 9, I'm sorry, 9 into 9, 81 constants would be required to relate each of these 9 stress components to each of the 9 strain components. But from our knowledge of symmetry of stress tensors, symmetry of strain tensors, and other strain energy considerations from continuum mechanics, we will see that such a matrix where there are 9, where there are essentially 9 rows. So we will see that many of these components will be independent of each other. So it will go to 0. That is how from 9 we come to 54, then 36, then 21. That delves more into continuum mechanics. I won't get much into that. But essentially, what we try to say is, from our first principles, what are the things that we know is the symmetry of stress tensor, the symmetry of strain tensor, and certain strain energy relations, because of which the number of constants needed to characterize that material will keep on reducing, which comes to 21 when we have a general isotropic anisotropic material. Now, from an anisotropic material, when we graduate to an orthotropic material, we know that the orthotropic material, the material properties at complementary angles are different. Orthogonal directions are different, which is why the name orthotropic has come. So using those relations, we will be further able to water down the number of constants required, which will come to 4. Then once we have that, we will see for a general isotropic material, and mind you, this says the minimum number of independent elastic constants required. So even for shear, in the case of an isotropic material, we only need 2 independent elastic constants, which could be any of the ones that we come across, be it the Young's modulus or the shear modulus or the bulk modulus or the Poisson's ratio. When we are able to evaluate any 2 of these for an isotropic material, we deem that we have been able to characterize that material. And we can, again, there are interrelationships which are also discussed in the lecture as to how we can evaluate the rest of the quantities. Once these are known, then this hurdle can be crossed easily from strains to stresses. So once I have some experiment, I know the displacement field, or from some analytical equation, I know the displacement field, I will directly come to stresses. I'll use that constitutive relation for that material. I'll get to strains and integrate to forces, and thereby relate these two in order for me to design the component. So for an anisotropic material, the number of elastic constants required comes to 21. This would also include Poisson's ratio in different directions. So that will Poisson's ratio also will become direction dependent, and there will be coupling meaning if I pull it, there will be change in distortion also. Not only change in the volume, that is, if for an isotropic material, for a let us say a cylindrical, let us say a square bar, I pull it, I will see that the cross section will still remain a square, but it will become less because of the Poisson's effect. However, in the case of anisotropic material, even if I pull, it could also lead to distortion of shapes, meaning that shear and normal strains will be coupled, normal stresses will be coupled. I hope that is clear. So, if a piece of material neither expands nor contracts in volume when subjected to stresses, then the Poisson's ratio is what? Is what is asked. So, let us delve a little bit here into what this means. So, let me just take. So, the question is asking that there is no volume change. Meaning, what this implies is I'm applying the stresses, but it is neither expanding nor contracting, so it is nearly incompressible. So for such a material, for such a rigid material, so to speak, what will be our Poisson's ratio approaching? For this, the approach we can take is we will see what happens in the case of a deformable, first of all, a compressible material. Then we can set that change to 0 and see how that comes about. So what happens when a body deforms? So let me take that same, in fact, let me take that same shape from here. Yeah. Let me put it here. Let us say that this is L. Let this be the breadth B, and let this be the height H. Now, under the action of some stresses, this has deformed to some. So in some way this has happened. I am not saying that it necessarily is volume, this thing. It has expanded like this. So what has happened is the new volume is L plus delta L. Let this be B plus delta B. Let this be H plus delta H. I am not constraining that delta quantity should be positive only. It may well be negative. That will depend on the problem, but I'm doing it for a general case. So now let this be subjected to sigma x, and let the coordinate system be like that. X, let this be, I'm sorry, a minute. Yeah, so let the coordinate system be like that. X, Y, and Z. So let this be subjected to sigma x in this direction, sigma y, and sigma z. I'm not drawing on the negative faces, but I suppose that is anyway clear. So in such a case, what is the volumetric strain? Or I should say the volumetric strain is the final volume minus initial volume divided by the initial volume. If we were to take our reference configuration, this is the general definition for any strain. Axial strain will be change in length by original length. So change in length is final length minus initial length and so on. So the final volume, so let me denote this by E wall, epsilon wall. This is nothing but my L plus delta L into B plus delta B into H plus delta H. So this is my final volume minus my initial volume is nothing but LBH, L into B into H divided by the same quantity. This thing. So this is our volumetric strain. So if I were to multiply this out, so this is LB plus L delta B plus B delta L plus delta L delta B into this quantity. This will come as it is. The other quantities come as they are. Here only this goes till here. Very well. So I'll again open this out. Granted, this might be obvious for the attendees and also might be overkill as to why we are multiplying this out when the answer is straightforward. But at least if we are suddenly we face the question and we are not able to remember, this is good to derive from first principles if we are not clear about it. So if I multiply this out, it comes to LBH plus, in fact, let me use the same color. It will be LBH plus LB delta H. So I'm multiplying each term by applying the distribution. L delta BH plus L delta B delta H plus B delta LH. Or I should write BH delta L plus B delta L delta H plus delta L delta B H, and the final quantity is delta L delta B and delta H minus our same LBH will come here. So I'll just put this here. The entire this thing divided by LBH. Now we can see from here so when we see here, these two terms will cancel each other out. So let me remove that. Let me put it in one line. Now if let us say my delta H or delta B or delta L for that matter is of the order of 10 power minus 3 mm or meter or whatever. If that is 10 power minus 3, then this quantity is 10 power minus 9. So we can safely disregard this quantity. So ignoring the smaller quantities, it comes to this much. Again, if this is 10 power 3, 10 power minus 3, this will be 10 power minus 6. So I ignore the smaller quantities, that is product of two differentials if I ignore. That is, if I take this nearly equal to 0, same goes for this nearly equal to 0 and this nearly equal to 0, then what am I left with? So this leaves me with, I'll just copy paste from here, this leaves me with these two quantities here and this one. So it comes to this 3 by LBH. By LBH. So let us divide this out, distribute and divide. I get LB H by delta H when I do only delta H by H will remain, LB will cancel out. So this is delta H by H plus delta B by B plus delta L by L, which is another way of writing this is epsilon Z plus epsilon YY epsilon XX. So therefore, this gives us that the volumetric strain is nothing but the trace of my strain tensor. This is nothing but the trace of my strain tensor. Now, for the case of a generalized Hooke's law, the generalized Hooke's law is written as the strain tensor. I'm writing it in slightly different form than what is given in the lecture, and then I will open it out and show that these are the same. This is nothing but 1 plus mu by E into the stress tensor minus trace of the stress tensor into the identity matrix divided by E. Only here there will be a mu minus mu by E. So 1 plus mu by E into the stress tensor minus mu into trace of E. Trace of E we know it is nothing but sigma xx plus sigma yy plus sigma zz. I we know what is I 1 0 0 0 1 0 0 0 1. Rest of these are simple constants. We know what is sigma xx. So let me just write that out in fact. So this is epsilon xx, epsilon xy, epsilon x z yz. This will be epsilon xz, epsilon yz, epsilon zz. This is equal to 1 plus mu by E into tau yz, sigma yy, sigma zz, and this will be tau. Sorry, this will be xz, and this will be yz. And it's a symmetric tensor, so I'll just put that here quickly. So that is this minus this quantity I have to write. So this is minus mu into the trace so this plus this into mu by E into 1 0 0 0 1 0 0 0 1. So that is all there is to it. Now we can see that from here the same relations come, that on expanding we'll get epsilon xx as epsilon xx will be this into this minus this entire term into 1. So 1 plus mu into sigma xx minus mu into sigma xx. So that will just leave us with sigma xx by E, which will be sigma xx by E minus mu. And since sigma xx is gone, sigma yy plus sigma zz by E. Similarly, it will go cyclically for the normal strains. So I can just quickly populate that, just so it is there somewhere. So this will be yy x z, and this will be Z, X and Y. This goes for the normal strains. Now for the shear strains, we can see that this quantity has to be multiplied by the off diagonal terms, which are 0. So this second quantity does not have any component that does not contribute to the shear strains. That is what this implies, because this is the identity matrix. So we can simply disregard this. So epsilon xy will be 1 plus mu by E into this quantity. As simple as that. So this gives me that epsilon xy 1 plus mu by E into tau xy. Similarly, the others also can be written. In fact, I'm just writing it for the sake of completeness so that everything is there at one place. So I hope you can bear with that. So this is xy. I'll just remove this. This will be x, z, and then I have to write for yz. So these are the relations that comes about. So if at any point we forget it, we just need to know this relation and we can easily write that out as to how that comes about. So given that epsilon xx, epsilon yy and epsilon zz are related in this way in terms of stresses, let us revisit the problem what we saw here. So we saw that volumetric strain is the sum of these three quantities. This was our volumetric strain. Now what I'll do, I'll just write it in terms of stresses. This, now writing the right hand side, in terms of stresses. So I have again E volumetric. So it will be the sum of these three. What this means is it is a sum of these three. So if I were to take the sum of these and collate the terms, I'll just do the collecting the terms simply. So in the first equation, sigma xx by E's coefficient is 1. In the second one, it is minus mu by E. In the third one, it is minus mu by E. So it is 1 minus 2 mu. So this is sigma xx into 1 minus, or rather, let me take 1 minus 2 mu out. So it will be 1 minus 2 mu by E into sigma xx when I added the x terms. Now let me add the y terms. I have y here, coefficient y, and then there is a third y here. So there will be, this will just be plus sigma yy going into the bracket. Same goes for sigma zz as well. So this is our, for what have we done for a cuboid or for any body for that matter. I have taken a finite body. We can take an infinitesimal body where we are applying some stresses in three directions, namely x, y, z, and then it has volumetric strains. It has a volumetric strain which is defined by this, which is nothing but the trace of our strain tensor. Now that replaced in terms of stresses gives us this relation. So this we can see it is nothing but a stress strain relation. It is just the inverse of that. So in fact, if I were to take it like this, so the sum of the stresses happens to be E upon 1 minus 2 mu into volumetric strain. So this is my stress strain relation in a general case which is subjected to only normal stresses. Now our question is asking, returning to the question, if a piece of material neither expands nor contracts in volume when subjected to stresses, then the Poisson's ratio is what? So in this equation, what it is saying is that when it is subjected to stresses, there are no volumetric strains, which means this is shooting up to a very large value. It is extremely stiff. So there it is not allowing any volumetric strain to happen. So therefore, if E upon 1 minus 2 mu shoots to a very high quantity, a very large quantity, if it tends to infinity, then the strains will naturally, given a stress state, naturally this will have to go to zero in order for us to have that correlation. In which case, then 1 minus 2 mu should be equal to 0, or mu should approach 0.5. So this is the conclusion we can draw from this, that when the Poisson's ratio of a material approaches 0.5, it starts showing no volumetric strains. Now if we see for rubber like material, even if we stretch it, its volume would still remain intact. Its volumetric change will be very less because its Poisson's ratio is quite high. I hope this is clear. So this Poisson's ratio approaches 0.5. Okay, so let us look at this question. Choose the correct statements. For isotropic materials, due to symmetry, shear components exist for thermal strains. So as we saw earlier, even from the second question which we saw, the strain tensor, the shear strain components do not exist. So this is incorrect. Thermal stresses occurred when the expansion of or contraction due to thermal strain is not constrained. So what this says, let us say that there is a block and there are supports like that. I just place this block in between two walls, let us say like that. The block is of length like this, and I have kept it such that it has its side touching with one of the walls. Now I increase its temperature. I know that it will, I'm talking in the plane of the paper, it will increase its volume, and up to this point it is a free expansion. That is, whatever I'm observing, observable strain is nothing but my mechanical strain plus my thermal strain. So till the point that I observe a strain due to temperature change, there won't be any mechanical strain induced into the material. It is only when the observable strain reaches a limit or is constrained, then when this goes to zero or some finite value, then beyond that, when I increase my temperature, naturally mechanical strains will start building up. So when I increase its temperature, ideally, what I mean to say is, if I increase its temperature, we generally consider only the length to increase because that is the dominant dimension. The out of the depth, so to speak, we are not presently considering. So with that argument, if I were to increase its temperature from here, it starts heating up and it reaches this point. Till that point, there is free expansion, so there would be no strains developed. Now, if I were to heat it beyond this material, beyond this position, so what would essentially happen is this can be broken down into two components. This can be broken down as a sum of two actions, where I will remove this support and I'll remove this support, let us say. So when I increase its temperature beyond this, then this would want to increase till that point by itself. If this is my, let this be that position. Now, due to free expansion, if the wall wasn't there, then this would have expanded till here. But now, since the wall is there, it will offer a reaction which will bring it back to 0. In fact, I should be putting the wall here. So now it will bring it back to 0. So there would be a compression. So this is free expansion. This point will become more clear when we solve one example problem that will follow. So this is free expansion. But since the free expansion does not happen, there is a reaction from the wall which will bring the observable strain to 0. And that reaction will induce a mechanical strain. So naturally in this equation, when the left hand side goes to 0, we can see that the mechanical strain is equal to the negative of the thermal strain. So the thermal strain would have been this much. So the mechanical strain in terms of this reaction has to nullify this in order to bring it back to the same position. So the thermal stresses, once mechanical strain comes about, then naturally from our constitutive relation we can get back to our mechanical stresses, which are also called thermal stresses when these come about because of thermal strains. So thermal stresses occur when the expansion or contraction due to the thermal effects is not considered. This is not true. Not constrained. I'm sorry. This is not true. When it is constrained, only then it will come about. Otherwise, we will have a case of strain without any stresses, mechanical stresses. Auxetic materials. Auxetics are materials with negative Poisson's ratio. So what does this mean, auxetic material? So there are a class of materials which are developed, synthesized, or which happen to have Poisson's ratio which is less than 0. So what does this mean? Let us say that I have a pipe like that. Now if I were to pull this, normally what in normal materials we will see is this D would actually reduce. But it so happens there are certain class of materials where when we pull it, because of Poisson's ratio. So how is Poisson's ratio defined? Ratio. Mu is nothing but minus of lateral by longitudinal. So this is to be kept in mind. So if my mu is negative, that implies that lateral strain also has to be positive. It has to be of the same nature as the longitudinal strain. Only then these signs will cancel out and this negative will get retained for mu to be negative. What this means is, for certain class of material, when we pull it along one direction, the dimension also increases along the other direction instead of decreasing. So those materials are called auxetics, and these are extensively being used in biomedical applications. For example, as it is discussed in the lecture also, for example, we place stents inside the bloodstream. So we want to widen uh, the artery where the clog is. So if we were to employ such a cylinder over there, a vessel over there, and if we were to pull it, and it automatically expands its diameter, so that will serve the purpose. So There are many interesting applications like this for such materials. So these are called auxetics. So auxetics are materials with negative Poisson's ratio. Yes. Wood is an orthotropic material. This we have seen umpteen number of times because of the distribution, because of the very nature in which the grains are aligned in wood, it makes it an orthotropic material. In isotropic material, shear stress component develops corresponding shear strain as well as normal strain. So the normal behavior and the shear behavior are decoupled in case of isotropic materials. These are not coupled. One doesn't cause the other. So this is incorrect. I hope it is clear. So are there any questions at this point? Okay, so I take it that everything is clear. So let us move forward then. Okay, so let us look at this question in the meantime. A steel rod with Young's modulus 220 GPa and alpha S, which is the coefficient of thermal expansion. So we have E of the steel as 220 GPa, and we have coefficient of thermal expansion as 1.2 E minus 5 per degree centigrade, having a length of 1 meter at a room temperature of 20 degrees, expands freely when the temperature is increased to 70. What would be the stress developed in this steel rod is what is asked. So we know that the observable strain is sum of the mechanical strain and the thermal strain. So the observable strain happens to be, since this is a free expansion, in this case, whatever is the thermal strain is what we are observing as well. So the mechanical strains go to zero, and consequently the mechanical stresses also go to zero. So this is a case of free expansion or free contraction. We do not have any stresses developed unless it is constrained. We will not have any stresses developed. So this is one case where even though a strain is present, the mechanical stress might not be appearing in our equations. All right. So let us look at this question. The greatest ocean depth measured is in the Challenger Deep of the Mariana Trench at a depth of 11,000 meters nearly. The pressure at the deepest point can be determined as P equal to rho GH, where rho is the density of water, G is acceleration, and height is whatever, that 11 kilometers. If one drops an aluminium square block with Young's modulus is 70 GPa and the Poisson's ratio coming to 0.33 offside, so we have a square block. So essentially what we are trying to say is it's a cube. We may as well have said a cube. So we have a cube of side 10 mm, which has been dropped there, and it has reached the point of that maximum this thing. So what is the magnitude of the volumetric strain experienced by this at the bottommost point? So in this case, there would be a compressive stress along all the axes, and that compressive stress will be nothing but my rho GH. So this is a case of hydrostatic compression. So now the volumetric strain is asked. So now we had it here that the volumetric strain is this much. So from here, the volumetric strain is this quantity into this by E. This is my volumetric strain. Now for this question, in this case, oh, where did the, yeah, in this case, I can see my sigma x, sigma y, and sigma z all are identical, and all are is equal to rho gh. Xx, yy, and zz is rho gh. So therefore, my volumetric strain comes out to be 1 minus 2 mu by E into 3 times of rho gh. So let us substitute that. 3 into 1 minus 2 into 0.33 by E is 70 GPa into rho G is 10 and the height is around 11 kilometers. So this is 10 and height is something like that. So this comes to into 3 by 73, 1 minus 2 into 0.33. So yeah, so this comes to 1607. Seventy GPa. Okay, this we have substituted it in meters. So GPa I will have to substitute it in, yeah, something was off, that's why. Yeah, it will be 70 into 10 power 9. Yeah, someone had any question? Yeah, so this will be 16. Yeah, yes, please.
70 e power 9 sounds too much for Williams. Typically, it's 70,000 MPa, isn't it? I 70 GPa.
Yeah, no,
So I
I'm
think 70
substituting
e
it in
power.
meter, that's why. Yeah,
Right.
yeah.
Sorry. Thanks.
So 1607.8 microstrain. So I encourage the viewers to check this in any case. So the volumetric strain comes to this much for that cube which is dropped in. Just a fictitious problem for us to be able to appreciate how to apply the equations. So I take it that is clear. In case you have any doubts, you please feel free to ask. In the meantime, let us move on to this problem of a compound bar with a load of P. This P is 220 kilonewton. It is applied as shown, and then it is uniformly heated over its length. If the temperature of the bar increases from 15 degrees to 48 degrees, then answer the following sub-questions is given. Let me take this entire setup and separate this out like that. So what I'll do, I'll take P and apply it here. Now that this has to be in equilibrium, so naturally there will be some reaction developed here because of the fixed end at A. Let us call that reaction Ra. Now, for this free body diagram to be complete, I need to account for its body force. But since the question doesn't speak of that, we will neglect that for the time being. And then call it 1. Let us call this 2. So there will be an interaction, force interaction setup, which let me put it like that. Or rather, let me take it to be in the same direction. So let this be R2, 1. Now when this comes to the other body, as we discussed in one of the previous sessions, when it comes to the other body, it will have to be R12, except it will be in the opposite direction because of Newton's third law. And then again here I should have applied the weight, but I'm not considering the weight presently. So for the second body to be in equilibrium, there will again be a reaction developed like that. Call this RC. Because this is C, I'm just naming it C. So now we have essentially drawn the free body diagram with all the components filled in. Is it necessary that this force would have to be this way? No, we have assumed it that way. And based on our computation, if it comes out to be negative, it would just imply that we need to reverse the direction instead of following the same direction. So far, so good. So for body 1, now that we know by Newton's third law that R12 is equal to minus R21, I can drop the subscripts here. So let me look at for the first body here. So for the first body, from equilibrium, I have sigma fx, call this x direction and that y direction. Since we are dealing only with an axial member, the x direction is sufficient. So sigma fx equals 0 gives us minus Ra plus P plus R equaling 0, or Ra equals P plus R. So this is one equation that I have got from the equilibrium of the first bar. Similarly, I can take this and apply sigma fx equals 0, which gives me minus R plus Rc equaling 0, or Rc equal to R. So from these two equations, I can see, I'll just name it as equation 1, and this is equation 2. From equations 1 and 2, we have Ra equaling P plus Rc, or Ra minus Rc equal to P. Now let us reflect what we have done here. Generally, what we used to do in a truss, we had a member that is subjected to an axial pull, and by method of joint or by method of sections, we used to find the reactions. Now I isolated the bodies, considering them to be rigid bodies, and I have written the equilibrium equations. There are essentially two unknowns in this question, Rc and Ra. These quantities we don't know. We, however, know what is P. Rc happens to be equal to R. This much we know. From applying just equilibrium equations, we have got one equation with which we are not in a position to solve for them individually. We only know this relation. So this is a statically indeterminate problem. I am not able to find the actual reaction distribution by statics alone, which is where I need to bring in now the knowledge of deformable bodies also. So let me take the same case, the same body, body 1, and let this hold for the time being. Let this be equation let me call it equation 3. All right. Now, here the observable strain Now the observable strain here, it will be mechanical strain plus the thermal strain. So let us see under the action of this force how this will deform. So this will, or rather this will have a total deformation. Let deformation of body 1, this is AB, I suppose, AB, yeah. The total deformation be delta 1. So delta 1 has a component because of the pull which is applied, which is nothing but RA into L AB upon A area of AB plus E AB. This is nothing but PL by AE, our same relation, where it is applied to subjected to an axial pull. Wherever this is subject to an axial pull, we know that uh, the change in length is given by RL by AE. Now comes the thermal part. Now we have been told that its temperature increases from 15 to 48 degrees. So what will this come out to be? Excuse me for 1 minute, please. I'm sorry about this. Hello. Hello. OTP on the 821288. 288. Okay, thank you. I'm sorry about that. So this is because of the axial pull, and then there is a thermal expansion. So because of the thermal expansion, what will be the change in length? So epsilon thermal is given by L alpha delta T. That is change in length by the length is given by alpha delta T, or the change in length is given by L alpha delta T. This is just an aside as to how this is calculated. So this will be nothing but LAB into alpha AB into delta T. So this is the total deformation of the first body, part, that is this composite aluminum composite bar. Its total deformation will be this quantity. Similarly, I can take for the second bar also. Let me take this. I'll write it here. For the second bar, let this be called delta 2. Let this be called delta 2, and this is BC. So delta 2 would constitute RC LAC by AAC EAC, where LAC is its length, this is the area, this is the Young's modulus, and this is also subject to a pull axially. So this thing will be expanding for now, considering this sign convention, plus LAC alpha AC into delta T. So we have got these two equations, how this freely expands and how this freely expands. Now what we know from the constraint of the problem is that delta 1 plus delta 2 is 0. Why? Because this could have expanded freely like that, this could have expanded further freely like that, but both are restricted because of this support condition. So these two essentially add up to 0. So this is the constraint equation. for this problem. Very well. Now substituting this, what do we have as delta 1? We have delta 1 over here. So I'll just take a copy of that. I'll put it here. This plus delta 2. Delta 2 I have derived it here. So I'll just take this and put it there. So what the constraint equation is telling me is the sum of these two is 0. Now what are the unknowns in this equation? We have RA, RC to be unknown. Rest everything is known. So we have two unknowns. We have one equation over here and one equation we had derived from statics which related RA and RC. So when there are two equations and two unknowns, now we can easily solve for them. It is just a matter of solving two consistent equations. So let this be, this is equation 3, let this be our equation 4. Now it is to be noted that this equation has come about only because we have considered the body to be deformable. So this problem could not have been solved if we did not consider this to be, if we did not bring in the deformation into the picture. So I'll call this equation 4. Now it is just a matter of solving. Equation 3 and 4. So let me bring that equation over here. So I'll just rearrange equation 4 a bit to match it in the same form. So this will be this term plus this term. These two terms equal minus delta t. If I take common, it will be this quantity plus this quantity. I have just taken those to the other side. I hope there is no confusion there. So now I have RA into some coefficient plus RC into some coefficient equaling some other value. Similarly, I have RA minus RC equaling some other value. So I just have to solve these consistently. So casting these two equations as a matrix equation, what we will see is this is 1, this is minus 1, RA, RC gives me P. So the first equation is, if I multiply this out, 1 into RA minus RC is equal to P. I have accommodated the first equation. The second equation, I just need to populate the coefficients. So this, but RA I have already taken outside, so I'll remove this. And then I have this. RC I have taken it outside, so this will also go. And the right hand side is just this quantity. I'll just reduce its size and put it here. So it is just a matter of substituting and solving this. So let us do that quickly in the interest of time. So this is just 1 minus 1. LAB. LAB from the question is, in fact, let me state it here. LAB is 40 centimeters. So for consistency, I'm putting it as 40 mm. Similarly, LBC is 250 mm. Area AB is 1200 mm squared. And then area of BC is 2000 mm squared. EAB it is nothing but steel. So this is, I'm sorry, this is aluminum. So this is MPa, 70E3 MPa. E of, in fact, it would have been easier if I took this itself with me. Yeah, I think this will save a bit of time. Okay. With this, let us populate this matrix. So I have LAB, AAB, EEB, which is 400 by 12E2 into 70E3. And this is 250 by 20E2 into 220E3 into the same thing. Gives me P. What is P given in the question? P is given to be 220 kilonewton in the question. So I'll just substitute for that. This is 220 kilonewton. So I'm converting that into Newton. And then I have this expression, this big expression. Delta T is given to be going from 15 to 48. So 48 minus 15 is coming to 33 degrees. So this is nothing but minus 33 degrees into LAB is 400 into 12.8 E minus 6 plus 250 into 6.5 E minus 6. Now it is just a matter of solving this matrix. So I'll just, we can do that using a calculator quickly. So this quantity will be nothing but the inverse of this. Inverse into this. So what does this come out to be? 611 minus 1. So this is 400 divided by 12E2 into 70E3. 250 divided by 20E2 E2 into 220E3. 6. This is 220E3 and this is minus 33 into 400 into 12.8 E minus 6 plus 250 into 6.5 E minus 6. So this gives me RA is minus 18.31 kilonewton and RC comes out to be minus 238.31 kilonewton. So far so good. So we have been able to solve for these forces. So RA and RB have come out to be negative, which implies that the direction which we assumed are to be reversed. So the directions which we assumed that RA would be pointing, in fact RA would be pointing this way and then this will be under compression instead of tension. I hope that is clear. So let us, now that we have solved for this, the reactions, let us look at the question. What is the magnitude of stress experienced in the aluminium rod when the whole system is considered? Whole system meaning the pull is applied, over and above that the heat is given. So in this case, RA is minus 18.31. So rod AB is subjected to it is subjected to minus 18.31 kilonewton force. So therefore, stress in AB is nothing but 18.31 E3 by its area. Area was given to be 12 centimeter square, which is 1200 MPa. So this will be 18.31 E3 by 1200. So this comes to 15.25. So this will be minus 25 MPa. So the magnitude is asked. So this will be, in fact, we should not decide based on this minus, because this is because by the virtue of this force, when we reverse the direction, we can see that initially we took all the members to be in tension. But the result has suggested that my force needs to be flipped, and by virtue of that flipping, the force has become compressive in nature, which is why the rod is subjected to a compression, but the magnitude of the stress is asked. Therefore, I will report just 15 point. So sigma AB is nothing but 15.26 MPa. Similarly, the stress experienced by the steel rod will be this quantity, sigma by steel. Steel rod is nothing but BC. Sigma BC is the magnitude of this. I'll remove the kilonewton. I'll substitute it by Newton. And the area was 2000, I think. So this comes to 238.313 by 2000, which is around 109.16 MPa. So we have solved for the stress, and both the rods are subjected to compression, which makes sense because it was eventually being pulled. The first rod was being pulled and the second rod was being compressed. Now the temperature has increased. So, but the free expansion is constrained. So it turns out that both the rods are subjected to compression of these varying amounts. So I hope that is clear. Are there any questions at this point? Anything that you want me to discuss? Okay, so I take it is clear. All right, so let us look at this question. An LPG tanker was investigated by a group of mechanical engineers as part of inspection using a reflection photoelasticity setup, which is missing, and identified a point where the stresses are high. So basically, they have coated this with a reflective coating, seen it with a polariscope, and saw that the stresses are peaking here, which is why we are now confining our attention to that point. It is decided to measure the strain at this location using strain gauges pasted as shown. So at this point, we have two strain gauges pasted. One is 1 and 2 with, so this is given to be z direction. So EZZ is given to be strain gauge 2, which is and then EYY is strain gauge 1. All right. So at this point, we have pasted two strain gauges, one along the z direction, one along the y direction. So we can make out that x is pointing into the plane of the paper, so that x cross y becomes z. For our convenience, we can also consider this to be x and y. In fact, I'm not sure if this is z or x. For the sake of convenience, why don't I take it to be x? For the purpose of the discussion, what I'll do, I'll take this axis as x and this as y. So the strain gauges are aligned. The strain gauge 2 is aligned along EXX and strain gauge 1 is aligned along YY direction. If the reading in the strain gauge 1, that is EYY, is given to be 250 microstrain, EYY is given to be 250 microstrain, and strain gauge 2, which is EXX, is given to be 50 microstrain. When this pressure vessel is pressurized from inside, if the steel tank, if I were to cut a cross section here, so this will be a thin cylinder which has some thickness. That thickness is given to be 10 mm, and its mean diameter, because of the thickness along the center line, if I were to take the mean diameter, comes out to be 750 mm. Answer the following sub questions considering E to be considering G, the modulus of rigidity, to be 80 GPa is what is asked. What is the value of the Poisson's ratio, the pressure inside the tank, the Young's modulus of the material, what is the Hooke stress, the longitudinal stress, and the maximum shear stress at this point. Based on our stress strain knowledge of our stress strain relations, we are supposed to derive these quantities. So let us see how to go about doing that. Yeah, any questions? Anyone had any questions? Okay. So from our previous discussions, if I just take this tank here, which is subjected to a pressure. Now if I were to cut a cross section here, I'll be seeing a circle like that, which has a, so this is given to be 750 mm, and then I have pressure that is acting on this. So in one of the previous sessions, we saw that for Hooke stress, what I'll do, I'll take the same thing. Let me remove this. Let me remove this. So this is subjected to internal pressure. Like that all over. So if I were to cut it in half, so this will expose my Hooke stress. So this is sigma h standing for Hooke, and this is my internal pressure P, let us say. So from the balance of forces, we saw that sigma h comes out to be P, and let this be the radius, the radius of the, let this be 2r. So this came out to be PR by T. So this was our Hooke stress component as per our previous discussions also. Now if I were to take instead, I take a longitudinal section. In this case, I take the same this thing, but this time I don't cut a section like that, but I cut a section, say like this, and see what I see. So what this will expose is sort of a rectangular this thing, which will have something like this. And then this is, of course, this is going beyond. I'm not drawing either ends. So here there is pressure acting on this face. This face is subjected to pressure inside the plane of the paper. And then we will have the longitudinal stress like this. Oh, I'm sorry. Again exposing the hoop, I suppose. Yeah, what I should be doing is I should, once that I cut a section like this, yeah,
I, I think it was fine. I think you just had to draw the arrows horizontally.
yeah, all right. Okay, so what I'll do is, so let me take a section like this. I'm not worried about that part. So here I have the longitudinal stresses and I have the pressure applied here. And when I cut this as a section, what I will be seeing is again the circle. So here from the balance of forces, what I will get is the longitudinal stress is applied throughout the periphery of uh, the thin cylinder. So the longitudinal force applied is P into pi r squared, and the resisting stress which develops in the wall will be sigma L into the area, which is nothing but my 2 pi r into my thickness of the sheet, which is this T. So therefore, from equilibrium, I have P pi r square is equal to sigma L into 2 pi r T, or my longitudinal force is nothing but P pi r squared by 2 pi r T, which gives me P by PR by 2T. Granted, this is also discussed in the lecture. So what this tells us is basically in a pressure vessel, I have two types of stresses. One is in a closed pressure vessel, I have two types of stresses. One is the longitudinal stress and one is the hoop stress. And hoop stress happens to be twice the longitudinal stress. So this much we know for now. Very well. So let us operate with this and move forward. So what we want to find is the Poisson's ratio. And what is the quantity that has been given to us is strains. So epsilon xx and epsilon yy are given. So from here we can see that the x direction is nothing but our length direction L, and the y direction is nothing but our circumference hoop direction. So this is nothing but my longitudinal strain, and this is nothing but my hoop strain. Now naturally, when my hoop stress is double the hoop strain, my hoop stress is double the longitudinal stress. Now I would expect that my hoop strain also will be greater than my longitudinal strain, which is reflecting correctly in our readings. Granted, it is not twice. Naturally, it will not be twice because of our Poisson's effect. So with that, let us proceed. So this much we know. I'll just make a copy of this. Okay, so this we know, and we have our hoop stress as PR by T, hoop strain, longitudinal stress as PR by 2T. So from our knowledge of constitutive relations, we know that epsilon xx is nothing but sigma xx minus mu sigma yy, and sigma zz is 0. So this is totally divided by E. Similarly, epsilon yy is nothing but sigma yy by E minus mu sigma xx by E. Let me write it in a similar fashion so that there is no confusion. All right, now it is just a matter of substitution. So in the question we have been given the modulus of rigidity instead of E. But from our interrelationships we know that G is nothing but E by 2 into 1 plus mu. I encourage the viewers to visit the lecture as to how this is derived. It is simple. We can derive it from our stress transformation equations easily. So therefore, E is nothing but 2G into 1 plus mu. So substituting all this, we will get sigma xx is epsilon xx, which is nothing but so this is my epsilon, sigma xx, this is sigma yy. So this is PR by 2T E minus mu times PR by TE. Similarly, epsilon yy will be this quantity without the nu, this minus mu into this. So these are the two relations. What are the unknowns? We have P is an unknown, the pressure. We have nu as the unknown. E is not as such unknown because we know that in terms of G and mu. Mu anyway is an unknown and G is given. And we have the strains here. That is already known. So let me just substitute those things. So this will become PR by, okay. So from here, what is 2TE? From here, it follows 2TE is nothing but 4G into 1 plus mu. 4GT into 1 plus mu. Similarly, TE is nothing but 2GT into 1 plus nu. So substituting this, I will get this quantity in the denominator here minus nu PR by TE, which is this, equals epsilon xx, which was given to be how much? 50 microstrain. So this is 50 into 10 power minus 6. The second equation will be this. And I'll just take this. I have to put a nu. And this will be 250. I suppose that was 250 microstrain. Now we can see there is a problem here that these things are coupled. It cannot straight away sit into a linear equation unless we we club certain things. So therefore, let us club certain things. Let PR or rather P by 1 plus mu. Let me define this quantity as some A, and let mu P by 1 plus mu be defined as B. So I will just recast with this with these relations. I will just recast this matrix equation. So it will be just this same quantity, except P and 1 plus mu will not appear. And this will be A minus mu P I'll remove and 1 plus, and this will be B is equal to 50 microstrain. Similarly, I will recast for this also. So here I can remove P and 1 plus mu and I'll call that as A. And here I'll remove mu P and 1 plus mu and call that B. I hope there is no confusion there. Okay, now it is just a matter of solving this matrix equation. So the coefficients are R by 4gt, R by 2gt, and then it is just the negative of this into AB gives me this quantity 50 E minus 6 and 250 E minus 6. Now R, what is R? R is, so this is 2 times of R, and that is given to be, in the question it is given, the mean diameter is given to be 750. So R is essentially 750 by 2, which is 375 mm. So in the question, R is 375 mm. G is given to be 80 GPa. Thickness T is given to be 10 mm. So therefore, this A and B, if I calculate, it will be the inverse of this. Inverse of this into this. So this comes out to be, I'll just solve this using the calculator. So this is 375 divided by 4. In fact, I'll write this here. 4gt, no? So 375 by 4 into 80E3 into 10. The same quantity will come here, except it will be negative now. The same quantity will come here also, except it will have 2 and negative now. Minus 2. Yeah, it is just a matter of solving this now. So let me just put it like this. 375 by 4 into 80E3 into 10 minus 375 by 2 into 80E3 into 10 minus 375 by 2 into 80E3 into 10. I'm sorry, here there won't be a minus. Minus 375.4 into 80E3 into 10. Very well. This is 50 e power minus 6, 250 e power minus 6. Inverse of this gives me 1.28. So this comes to 1.28 and this comes to 0.4266. So what have we defined A as? This quantity was A. So this has come to 1.28. And the quantity B was this. This was B. So B has come out to be this much. So from here, I just have to solve it further. So from here I can write P upon 1 plus mu is 1.28. So therefore, substituting these two, I'll get mu 1.28 mu is equal to 0.4266, or mu comes out to be 0.4266 by 1.28. So this comes to 0.33. So this is our Poisson's ratio. And the second quantity, from here we can calculate, if this is 1.33, therefore pressure will be 1.28 times of 1 plus 0.33, which is 1.33, 1.28. So this comes to 1.7. So the internal pressure is 1.7 MPa inside the tank, whose Poisson's ratio is 0.33. Makes sense. So the pressure inside the tank is this much. We have solved for that. Pressure is this much. The Poisson's ratio was asked somewhere. It is this much. The Young's modulus E, we know it is 2g into 1 plus nu, which is 2 into 80. Since it is asked in GPA, I am not putting 10 power 3. So this will come to 2 into 80 into 1.33, which comes to 212 GPa. This is our Young's modulus. What is the Hooke stress? We know Hooke stress is PR by T, and the pressure came out to be 1.7 MPa into 375 was our radius divided by 10. So this comes to 1.7 into 375 by 10. So this is coming out to be 63.75 MPa. And the longitudinal stress is asked. We know that the longitudinal stress is half of the Hooke stress, which will be nothing but 31.875. The maximum shear stress at this point is asked. So we know that in this case, because of the symmetry of the problem, there are no shear stresses, in which case my Hooke stress and longitudinal stress are my Hooke and longitudinal are my principal stresses. So for this problem, if I draw the Morse circle, I have 63 here, I have 31 here. So let me draw one more circle as this. The other one is like that. Actually, it will also be a little bit smaller. And the third one will be enveloping these two. So what is the maximum? So the maximum shear stress here is, this point is 63.75. So therefore, the maximum shear stress is the radius of the bigger Morse circle, which is nothing but 63.75 by 2, which happens to be 31.875 MPa. This is the maximum shear stress experienced at that point. I hope this is clear. Had this question given us E directly, we wouldn't have been required to go through such a circuitous route to find, but this gave G instead of E. So as engineers, we should be comfortable in maneuvering between the elastic constants. So that is how we have addressed this question, and we have been able to obtain the material property, internal pressure, and the Hooke stress and longitudinal stress. So I've run out of questions. Are there any questions at this point? Anything you want me to discuss? Okay, then we'll catch up on Friday if possible. Otherwise, anyway, we will be joining on the sessions to come in the future.
All right.
So I thank you for attending. So I'll see you guys next week on Friday.
Yeah.
Yeah, yeah.
Speak to you.
Okay.
Bye-bye. Thanks.
Bye. Good night.
Good night.